Hello and welcome to the first video for our online version of MATH-221. This is very exciting. So let me just say a few words about how this is going to work. I'm just going to try to do exactly what I used to do in class. So I'm going to show you slides with some of those important key facts from the textbook sections. And I do expect that you have already read the textbook sections, so you're familiar with the material already. I would suggest that if you have a poor internet connection and you're not able to watch these videos well, that you could just substitute reading the textbook sections for watching the videos. And then after I explain some facts, we'll do some examples, and then I'll have slides where the homework questions are, and then I'll ask you to pause the slide, pause the video, and do the homework problems. And I think it will be best for you from a pedagogical perspective if you really actually pause at the times when I tell you to, and do those homework problems. And then as usual, you'll be able to check your homework problems. The solutions will be in the back of the textbook. A few words about other things. So if you are having trouble understanding something, you want to ask me a question, you can send me an email. And then by email, we can also set up a video chat. So that's what I'm going to be doing for office hours, just video chats over Zoom. And during those, we'll have a whiteboard space where we can both write on, and you could share your screen with me and things like that if you want to ask me about the quiz, for example. The quizzes are going to be up on Blackboard. They'll be either multiple choice or fill in the blank kind of drop-down menu type of things, or I might have some where you have to actually write something on your own paper and then take a picture of it or scan it and then turn it in through Blackboard. I hope and I plan to have all of the old quizzes up this week so that you can keep making corrections on your old quizzes and getting the higher scores on those. As for the new quizzes, you'll be able to try them on Blackboard as many times as you would like to and resubmit them until you get the score that you want. Okay, so let's get into this video. Okay, so we're going to do section 6.1, which is set theory, definitions, and the element method of a proof. Now, we did the first part of this section on the day before spring break. Most of you were not there, so you're definitely going to have to go back and read about all of that in the textbook. It's a really, really crucial and important section. All of the things in this section are totally basic and fundamental to every area of math and computer science. So it is not a section that you want to be weak on. Right, so let us pick up with where I left off on March 6th, which was the Friday before spring break. Okay, so we had just, I think, finished doing the set operations, which are the union, the intersection, the complement, and was that all of them, I think? And so next thing is the empty set. So the empty set is a set that appears in a lot of places. There are a lot of sets that you could just write down that turn out to not have any elements. So it is convenient to have a notation for the empty set. So if you didn't have a notation for it, then you would just write it like this. But we do have this other notation for it, which is here. You want to be sure not to mix up that symbol with other things that look quite similar, like phi or theta or the number 0. So a couple of examples of sets that are actually empty. The first one here says all the elements in the real numbers, which when they're squared equal -5. And of course there aren't any real numbers like that, so that is empty. And then the second example here, if we take the intersection of two sets that have no elements in common, so there's nothing in common to these, then their intersection is going to be empty. Okay, let's do some more examples from the homework problems. Okay, so here is a homework problem number 18, and I'm going to do number C, or part C and part D for you. So let's look at part C. Okay, so the question is the empty set an element of the set containing the empty set? So this is going to be true, and it's true for exactly the same reason that, for example, X would be an element of the set containing X. So any statement of this form will be true. So here you just have to be careful about the way the notation works. Whatever you have on the left side here It just needs to be inside the braces over here, and then that statement will be true. Okay, let's look at part D. Is the empty set an element of the empty set? This is not true. So the empty set is not an element of the empty set. So there are no elements in the empty set. So any statement of that form would always be false. So any statement of this form right there will be false. Okay, so now is a good time for you to pause the video and try to do part A and part B, and I'll just remind you that the solutions for those are in the back of your textbook, so you can check those and make sure you got them correct. Okay, let's look at another example. So in this one, we're being asked to draw a Venn diagram for sets A, B, and C that satisfy the given conditions. So I'm going to do part B. So let's look at the conditions here. So we want C to be a subset of A. So in other words, C is going to need to be a little circle that's inside of the A circle. So I'll just go ahead and draw that. Okay, so this can be C, and then this is A. Okay, and then we also want B and C to have an empty intersection. So there's quite a few ways that we could draw this. We could draw B in here, like this. Or another way to draw this could be, here's A, C is inside of A, B could be out here like this. Or a third way to do it we could have B partly in A and partly outside of A, like this. Any of these ways would be fine, just so long as B and C are not overlapping at all. Okay, so now is a good time to pause the video and you go ahead and do part A and then check that solution in the back of the textbook. Okay, let's look at number 15 here. I'm going to do part B for you. So part B, we need to draw A is a subset of B, C is also a subset of B, and we're being told that the intersection of A and C is not empty. So the fact that A and C have a non-empty intersection means that they do need to overlap a little bit. So let's try drawing this. So A is going to be inside of B, C is going to be inside of B, A and C overlap a little bit. So here's B that contains both A and C, and I can put A here, and then I just need to make sure that C overlaps with B a little bit, or sorry, with A a little bit. Okay, and now let's look at part C. This one has a lot of stuff in it. So this says A and B have a non-empty intersection, so A and B are going to overlap a little bit. B and C also have a non-empty intersection, so they are going to overlap a little bit. On the other hand, A and C do have an empty intersection, so they are not going to overlap at all. And finally, A is not a subset of B, and C is not a subset of B. So A is not completely contained in B, and C is also not completely contained in B. So let's try drawing this. So using the first one here, A and B need to overlap a little, but they can't overlap to the extent that A is actually inside of B. So I'm just going to do it like this, A, B. Okay, so that took care of this first one and the second to last one. And then I'm going to do C. So B and C need to overlap at least somewhat, but they can't overlap to the extent that C is actually inside of B. And then finally, I also need to draw A and C not overlapping at all. So I'm just going to put C over here. And with that, A and C do not overlap. B and C have a non-empty intersection, and C is not a subset of B. Okay, so now you should pause the video and try doing part A and check the solution. Okay, so our next definition is going to be disjoint. Two sets are called disjoint if and only if they have no elements in common. So symbolically, if you know that A and B are disjoint, that means that their intersection is empty. And the other way around as well, if you know their intersection is empty, that means A and B are disjoint. So if we were to draw a picture of that, it would just look like this. A has no overlap at all with B. Okay, let's do some examples. Okay, another definition to do with disjoint is that you can have multiple sets that are mutually disjoint or pairwise disjoint or non-overlapping. And this is the same as the last definition, it's just for more sets. So you can have a whole bunch of sets, A1, A2, A3, and so on and so forth, and they will be mutually disjoint if and only if any two sets in that group, like AI and AJ, which are actually distinct from each other, if they have no elements in common, then they will be mutually disjoint. So to say it symbolically, AI intersection with AJ is empty whenever I does not equal J. Do you understand why they have to specify this part right here? Because if they didn't put that, then you could have both I and J being the same number, and then of course a set's intersection with itself will be itself. So that's the reason why they have to specify that. I can draw you a little picture here. For example, A1, A2, A3, A4. This is a set of mutually disjoint sets. Okay, and now let's do an example. Okay, let's look at example 20 here. So we have BI is defined as all the elements x in the real numbers such that 0 is less than or equal to x and x is less than or equal to I. And then I can be any one of these four integers here, 1, 2, 3, or 4. So before we do part A, B, or C, I think we should specify exactly what are B1, B2, B3, and B4. So let's just plug in those values for I. So for B1, we're just plugging in 1 for I. So I'm going to get x in the real numbers such that 0 is less than or equal to x, which is less than or equal to 1. So plugging in 1 for I. And then I'm going to do a little illustration of it here on the real number line to help you visualize it. So here's 0, 1, 2, 3, 4. And this is going to be all the numbers from 0 up through 1. And I'm doing those solid dots there on 0 and 1 to include those numbers. If I was to use open dots, then it would not be including 0 or 1. Okay, B2, I'm just plugging in 2 for I. So this is going to be x in the reals such that 0 is less than or equal to x, which is less than or equal to 2. So plugging in 2 for I this time. And let's make the same illustration here. 0, 1, 2, 3, 4. And this time I'm going from 0 to 2. And then B3, same way. Okay, I'm going to go from 0 up to 3. And finally B4, plugging in 4 for I. illustration. Sorry, I'm getting used to using this computer pen here to write on the screen. Okay, so this is going to go from 0 up through 4. So I'm just coloring in everything between. A little sloppy. Okay, so you get the idea of what B1, B2, B3, and B4 are. So now let's try to answer the questions. So for part A, the union of B1, B2, B3, and B4. So the union is going to be all of the elements that are in any one of these 4 sets. So anything that's in B1 or B2 or B3 or B4, that is the union. And I think you can see by looking at the illustration that that is going to be B4. So B4 includes everything that is in any of those sets. Okay, part B, the intersection. So the intersection is going to be anything that is in B1 and B2 and B3 and B4. You really want to think of the union as just like the word or, and the intersection is just like the word and. So we're looking for things that are in all 4 of these sets, and hopefully you can see from the illustration that's going to be B1. B1 is included in every single one of those sets. Finally, part C, are these 4 sets mutually disjoint? So if they were mutually disjoint, that would mean that every pair of them had no elements in common. In other words, none of these sets would overlap at all. So that's definitely not the case, right? No. In fact, every pair of these sets overlaps. So again, if they were mutually disjoint, that would mean there was no overlap between any of these 4 sets. Okay. Okay, so here is your next homework problem. It's similar to the last one. So go ahead and give that a try. Now keep in mind here, it's not an inequality. It's literally just these 2 numbers that are in the set. Just those 2 numbers. Okay, so for like example, for A1 is just 1 and 1 squared, which is really just 1. Okay. Okay, now let's look at the next definition, which is a partition. So if you have a finite, or it could be an infinite collection of non-empty sets, A1, A2, A3, etc., that is called a partition of a set A if and only if the following 2 conditions are true. So A must be the union of all of the AI. So these sets right here in this list, they have to have a union of A. And then the second condition, the sets A1, A2, A3, etc. must be mutually disjoint. So you have to have a collection of non-overlapping sets that all union up to the set A. And if you have that, then this collection is called a partition of the set A. So let me just draw an example of what this would look like. So if we have A here, this is A. A partition is kind of like what you would think of as a partition in everyday language, like you're dividing up A. So for example, it could be divided up like this. This could be A1, this could be A2, this could be A3, this could be A4, A5, and A6. And then there would be no overlap at all between any of A1, A2, A3, A4, A5, or A6. And then their union together would be A. That's a partition. So for another example, let me just do a little toy example here for you. We could have A1 be the set containing 1. A2 could be the set containing 2. And A3 could be the set containing 3. And this is a partition of the set 1, 2, 3. Okay, so in a partition, you take some bigger set like this one, and you just divide it up into smaller pieces that don't overlap with each other. That's a partition. Okay, so let us look at some examples. So I'm going to do B, C, and E, and then A and D are your homework. So let's look at part B here. So they're asking us if these three sets, WXV, UYQ, and PZ, are those three sets a partition of PQUVWXYZ. So we need to check the first condition, which is that the union of these three sets gives us the larger set. Is that true? So did we cover all of the elements in the larger set? So let's just check. Did we cover P? Yep, it's here. Did we cover Q? It's here. U? It's here. V? It's here. W is here. X is here. Y is here. And then Z is here. So we covered condition 1. So that's good. And then the second condition is we need to make sure there's no overlap between these three sets. Okay, so if we look at those, do we see any elements that are in common between them? I don't think so. I mean, I only circled every element once, so I don't think there's any overlap. And so this will be a yes. Okay, so let's look at part C. So looking at this set here, 1, 2, 3, 4, 5, 6, 7, 8, we need to make sure that these smaller sets cover all of those elements. In other words, that their union is the numbers 1 through 8. So let's just make sure we got everything. Did we get 1? Did we get 2? Did we get 3? Did we get 4? Did we get 5? Did we get 6? Did we get 7? And did we get 8? Okay, so the union of these four sets is the larger set, but I think I already see a big problem right here with this number 4 that I didn't circle. That is being replicated. Okay, so 4 appears twice. So this is not going to be a partition. Okay, because 2 of those sets are overlapping. Okay, let's look at the next one. Part E. So let's just make sure that we covered all of these numbers from 1 through 8. So 1 is here, 2 is here, 3 is here, 4 is here, 5 is here, 6 is here, 7 is here, and 8 is here. And I don't see any numbers other than those, so I don't think we have any overlaps. So this will be a partition. Okay, go ahead and do part A and part D and check your answers in the book. Okay, now let's look at the definition of a power set. So a power set is like an operation that you do to a set. So you start with some set A, and then the power set of A, which is denoted in function notation like this. This is a script P. What that is, it's the set of all subsets of A. So let me just give you a quick example. If A was, for example, X, Y, just those two elements, then I'm going to write my script P like that. Power set of A. So what you have to do, put curly braces, and then you're just going to list every possible subset of A. So I'm going to start with the smallest possible subset and work up to the largest possible subset. So the smallest possible subset would be the empty set, which we have this notation for. And then the next smallest would be subsets that have one element each. So we could have X, we could have Y, and that's all the one element subsets. And then the 2 element subset would be A itself. Okay, and that's all the possible subsets. There can't be any larger ones. Yep, so let's look at some more examples. Okay, so this is actually your homework problem. So what you need to do in this one is first work out what, for example, A intersection B should be, what A union B should be, and then do the power set from there. You can do part B exactly the same as what I just did on the last slide. Now part D here, the Cartesian product, you might have a little difficulty with that, so maybe I'll do a little example at the top here just to show you what that might look like. So let's do an example with the Cartesian product. let's say I have set S containing the letters A and B, and then set T maybe contains the letters, maybe just the letter C. Okay, so then what is S cross T? Cartesian product of S and T. This is all of the ordered pairs where the first element comes from S and the second element comes from C. So in this case, I've made it a little bit easy for myself. I can only have either AC or, oops, I have to use my eraser for the first time. Okay, or I can have B, C. So it's the only two ordered pairs. Okay, so here's my set S cross T. It's just two elements, so the way the power set is going to work is just going to be exactly the same as in the last slide, where I also had a set with two elements. So power set of S cross T. So I can either have the empty set, or I can have a subset of one element, or I can have a subset with the other single element, or I can have a subset with both elements. Then I think of those ordered pairs as just really being single blocks. Like, don't look inside the ordered pair. Just think of it as one element, because it is. Okay, so that's the power set there, and you can do part D the same way. Okay, let's look at our next definition, which is ordered tuples. So, you're already familiar with the concept of ordered pairs from your math education. You know, ordered pairs, like in the XY plane, you have, you know, for example, you have X here, you have Y here, and then you could have a point here, maybe it's the point 1, 2. That's an ordered pair, so you've already learned quite a lot about those. And the only difference with ordered tuples is that you just have more numbers inside the parentheses. Okay, so you can have n elements in the parentheses, where n can be any positive integer. So it could be 1, could be 2, could be 3, could be whatever. And then you just have a list of numbers, which we're calling x1, x2, ... xn. And they do not need to be different, they can be the same. And the ordered n tuple, which is written like this, you just write all the numbers in parentheses with commas between them. It just consists of those numbers, and then also there is the ordering of the numbers. So the ordering is important. So x1 comes first, x2 comes second, and then so on and so forth up to xn. So it's not like a set where the order doesn't matter. With an ordered tuple, the order does matter. Okay, and then you already know that if you just have two numbers, that's called an ordered pair, and then if you just have three numbers, that's called an ordered triple. And I guess you could go on and talk about quadruples and quintuples, but we usually just call them tuples after that. So if you want to say that two ordered n tuples are equal to each other, so if you have two of them, and the first one is using x's and the second one is using y's, those are going to be equal if and only if each and every element within them in the order is equal. So in other words, the first elements have to be equal, the second elements have to be equal, and so on and so forth up to the last elements. Just like you would think. I mean, if somebody had asked you what it meant for two ordered tuples to be equal, I think this is what you would tell them. So symbolically, if we're going to say that x1, x2, ... up to xn is equal to y1, y2, ... up to yn, that simply means that x1 equals y1, x2 equals y2, so on and so forth, up to the last one, xn equals yn. And in particular, if you want to apply that last part about equality to an ordered pair, an ordered pair AB is equal to an ordered pair CD if and only if A equals C and B equals D. So it's like pretty straightforward, I hope. Okay, so now let's talk about the Cartesian product. So we had done this already previously, but we had only done it for pairs of sets. So we had only done like A cross B, for example. Well, you can do the Cartesian product for as many sets as you want to. And so the way it works is using that definition from the last slide of ordered n tuples. So if you have a bunch of sets, A1, A2, up through AN, then the Cartesian product of those sets, A1, A2, up through AN, it's going to be written, denoted like this. So you just put the times symbol in between all of them. And that is going to consist of all of the ordered n tuples A1, A2, up through AN, where, this is the important part, where the element A1 is from the set A1, the element A2 is from the set A2, and so on and so forth up to the last set. Okay? So it works just like the Cartesian product that we'd seen before, but just with more sets. So if we want to say it symbolically using set builder notation, this is A1 cross A2 cross ... cross AN is equal to the set of all ordered n tuples, where each element is coming from each set in order. And in particular, you can look at this definition down here. This is the same as what we'd done earlier in the class. Okay, so let us do some examples using that definition. So number 35 here, I'm going to do part C and part D. So let us look at part C. Okay, so we're supposed to do A cross B intersect C. Okay, so I'm just going to fill in what these sets are just to start out. So I'm going to substitute their definitions. This is A and B cross 1, 2 intersect 2, 3. Okay, and then I'm just going to try to simplify it. So I'll start inside the parentheses by doing the intersection first. So the intersection of 1, 2 with 2, 3, the overlapping element there is 2. And once I've done that, I can drop the parentheses. So this is just going to be the set containing 2. Okay, and now I'm just doing the Cartesian product of the set AB with the set 2. So this is going to be all ordered pairs, where the first thing in the ordered pair comes from the first set, and the second thing in the ordered pair comes from the second set. So these are my only 2 ordered pairs that I can make. And that's it. Let's try part D. So part D is a little more tricky, I think. Again, I'm just going to substitute everything from the definitions. So this is going to be AB cross 1, 2 intersect AB cross 2, 3. Okay, and now I'll just try to simplify. So I'm going to do the inside the parentheses first. So I'm going to do the Cartesian product of AB and 1, 2. So hopefully you can figure out that there should be 4 ordered pairs that you can get, because there's 2 things in A and B, and there's 2 things in 1 and 2. So you have 2 choices for each element. Okay, so I'm going to need 4 ordered pairs. I'll do the ones that start with A first, just to keep myself organized. Then I'll do the ones that start with B. I always try to list these things in an organized way. Okay, and then I'm going to do intersect. And now I'm going to do the other Cartesian product. So I'll do it the same way. I'll do the ones that start with A. And then I'll do the ones that start with B. Okay, and now I need to perform the intersection. So I need to look at things that are in both sets. And remember, there's only 4 elements in each of these sets. Like this is 1 element, this is 1 element, this is 1 element, this is 1 element. Don't try to drill down into those ordered pairs. The ordered pair is like a block. Okay, so what are the things that I have in common here? So I don't think that this ordered pair is in both sets, so I'm not going to keep that one. This one, A and 2, that is in both of them, so that's going to go in my intersection. A2. B1, I don't think that's in both of them, so I'm going to take that out. B2 is in both of them, so that's going to go in my intersection. Okay. A3, that's not in both of them, and B3, that's not in both of them. Okay, so my intersection is this, just A2 and B2. And now what's interesting here, if you look at this, these are actually the same. Part C and Part D, they're the same. Not a coincidence. I'll let you think about that on your own time. Let's go to the next slide. Oh, you should stay here and do Part A and Part B, of course, and check those answers. I'm going to go to the next slide. Okay, so let us look at section 6.2. I do apologize, I'm cramming quite a bit of material into today's lesson, but because we had that extra week of spring break, I did have to do a little squishing here, and the rest of the squishing is just the fact that we're not going to need work days now that we're doing online classes. So I think the rest of the material is going to fit it at more or less the same pace. Okay, so let's do section 6.2. This is properties of sets. Okay, so first let's look at some subset relations. So the first one is inclusion of intersection. So for any sets A and B, doesn't matter what they are, any sets A and B, the intersection of A and B will always be a subset of A, and the intersection of A and B will always be a subset of B. If you think about this for a while, it should make sense. Let me just draw you a little picture over here. So if we have A and B, here's A, here's B. Their intersection is this area right here, so it's everything that's in both of them. That intersection area is contained within the A circle, and it's also contained within the B circle. So it's a subset of A and it's a subset of B. Should make sense. Now let's look at the second part, so inclusion in union. So for all sets A and B, A will always be a subset of A union B, and B will also always be a subset of A union B. So this is another one that should make sense to you on some kind of intuitive level. Let's look a little picture of it. So here are sets A and B. And the union of A and B is all of this. It's the double bubble. Okay? So it's everything that's in either set. And if you look at this picture here, the set A is a subset of that shaded union area, and the set B is also a subset of that shaded union area. Okay, and let's look finally at the last one here. So for all sets A, B, and C, if A is a subset of B and B is a subset of C, then A is a subset of C. So this is another one that it should make some kind of intuitive sense to you. So let's try drawing a picture of it. So if A is a subset of B, that means A is inside of B. So here's A, here's B. And if B is also a subset of C, that means B is inside of C. So here's C. So you can't draw those first two conditions that are on the if without making that then part come true. So if A is a subset of B and B is a subset of C, there's no way to draw that without also having A be inside of C. Okay, so this slide is the procedural versions of set definitions. So previously in section 6.1, we had looked at the definitions of the union, the intersection, the minus, complement, and previously in the class we had also looked at Cartesian product, which is number 5. And on this slide, it's just reminding you what it means for X to be an element of any of these sets. And this is going to be very helpful to you when you're writing proofs that involve these set operations. So if X is an element of big X union big Y, that means that X is an element of X or X is an element of Y, and vice versa. So this little double arrow here, this is the if and only if. So if you know that X is an element of X or you know that X is an element of Y, that then also implies that X is an element of X union Y. And it's the same for the rest of these definitions. Little x is an element of big X intersect big Y, if and only if. Little x is an element of big X, and little x is an element of big Y. So when you encounter the union symbol and the intersection symbol, you really want to think of those as meaning or and and. And then the minus, x is an element of X minus Y, means that X is an element of X and x is not an element of y. Complement, x is an element of big X complement. That means that x is not in big X. And then finally the Cartesian product, xy, the ordered pair xy is an element of x cross y, means that little x is an element of big X and little y is an element of big Y. So these are the definitions that are going to be really important and key when you're writing proofs to do with set operations. Okay, so I'm about to present you with a really long list of identities for sets, so it's good to first remember what an identity actually is. So an identity is simply an equation that is universally true for all elements in some set. So for example, there are a lot of identities that you're already familiar with, and this would be one of them. A plus B is equal to B plus A. That is an identity that is true for all real numbers A and B. It's actually true for other sets as well, but it is true for all real numbers. So now I'm going to show you this really long list of set identities. Okay, so here is our list of 12 set identities, and this may look familiar to you, especially if you look at the names of these. These are coming exactly from the same names that we had for the logic identities that we had looked at earlier in the semester. So the commutative laws, associative laws, distributive laws, identity laws, they all come exactly from those logic identities. And it's not just that they're similar, like the reason these are true is because those ones were true. And these set operations are defined in terms of logic, like in terms of ands and ors and nots. So these are directly related to those. So let's just go through these and I'll say a little bit about each one. So the first one, the commutative laws. Oh, I should actually start up here. So just make note that all the sets below, we're considering them to be in some universal set U. Okay, let's look at the first one, the commutative laws. So this one is just telling you that you can do unions and intersections in either order. Doesn't matter what order you write the sets in. Should be pretty clear, I think. The second one, the associative laws. So if you have 3, or it could even be more than 3 sets, and you're taking the union between all of them, it doesn't matter what order you do that in. You could do A union B first, you could do B union C first, you could do A union C first. Doesn't matter. And same for intersections. It doesn't matter what order you do the intersections in. You could do A intersect B first, you could do B intersect C first. It doesn't matter. And in fact, because of that, we usually don't even write the parentheses like they've got it in these two laws, because it is associative. Now, on the other hand, the distributive laws, if you're going to mix unions and intersections together, you've got to be really, really careful that you get the parentheses exactly where you want them, so that you don't mess up the result that you get. Because, for example, in general, A union B intersect C is not going to be the same thing as A union B intersect C. Not the same at all. I think we talked about that concept when we were talking about ands and ors, that you also have to be careful if you're mixing your ands and your ors together, and it's the same reasoning behind it. So if you do have an expression like this where you have A union on the outside of some parentheses, what you can actually do is distribute that to the things that are inside the parentheses. So then what you end up getting is A union with B, A union with C, and then this operation that was inside here is going to be the same. Okay, so same deal down here. You have A intersect. You're distributing that to B and to C. And then the union symbol here is going to go between. Okay, so those are the distributive laws. And then the identity laws. So for any set A, if you union A with the empty set, well, that's not going to add anything. So you're just going to have A again. Doesn't do anything. Same deal if you intersect with the universal set. So here we're saying that all the sets here are subsets of the universal set. So if you intersect A with something that it's already a subset of, you're just going to end up with A again. Okay, the complement laws. So unioning A with its own complement. Remember, the complement of A is everything that's not in A. So this is A union with everything that's not in A. Well, that's just going to be everything. Like everything is either in A or not in A. So that gives you the universal set. And then the other way around, if you intersect A with the complement of A, this is everything that's in A and not in A. Well, there's nothing that's in A and not in A, so that's the empty set. Okay, let's look at number 6, double complement law. So here it's just saying that if you do the complement twice, it undoes itself. So things that are not in A are in A. So if you do the complement twice, you just get back the original set. Next one, idempotent laws. If you union a set with itself, it doesn't do anything. Intersect a set with itself, doesn't do anything. It's just the set again. It's kind of obvious. Universal bound laws. So if you union a set with the universal set is larger, so you're going to end up with the universal set. Okay, so this is everything that's in A or in the universal set, and we already assumed that A was in the universal set, so you're going to end up with the universal set. The other way around, if you intersect A with the empty set, so this is going to be everything that's in A and in the empty set, but there's nothing that's in the empty set, so you're just going to end up with the empty set. De Morgan's laws, so these work exactly the same way they do for logic. So if you take the complement of a union, that's going to be the intersection of the complements. Or if you take the complement of an intersection, that's going to be the union of the complements. And De Morgan's laws here are true for the exact same reason that they're true with logic. So look at what we've got here on part A. This is all of the elements that are not in either A or B. So if you're not in the union of A and B, then that means you're not in A and you're not in B. And for the second one, if we take the complement of the intersection of A and B, we're looking at things that are not in both A and B. So if you're not in both A and B, then you're either not in A or you're not in B. Okay, let's look at number 10, the absorption laws. So here, if you union A with an intersection that already has A in it, you're going to end up with just A. This one is maybe a little tricky to think about, so let me try drawing you a picture of number 10, part A. So I've got A and B. Here's A. Here's B. So the intersection of A and B is here, and then A is here. So I'm taking the union of A with the intersection of A and B. So I'm unioning everything that I've colored right now together. And you can see that it's going to just be this circle of A. If we look at 10B, it's, 10B is quite similar. So let's do A and B. Okay, so we're taking the intersection of A with the union of A and B. So the union of A and B is all this, and then we're intersecting that with A, which is here. So we're looking at the things that have been shaded in both directions. So the union of A and B is this way, and then A is this way. The intersection of those two things is the things that have been doubly shaded, and it's just A. Okay, complement of the universal set and the empty set should make, I hope, complete sense to you. Everything that's not in the universal set should be nothing, because everything is supposed to be in the universal set. So the complement of the universal set is the empty set, and then everything that's not in the empty set is going to be the universal set, because everything is not in the empty set. And this is everything. Set difference law. So saying the difference of A and B, A minus B, this is everything that's in A and not in B. And this is just another way to say it right over here on the right, everything that's in A and not in B. Okay, so let's look at some ways to prove that sets are subsets of each other or that they're equal to each other. So let's say that we have two sets x and y, and we want to prove that x equals y. So there's two steps. First you prove that x is a subset of y, and then you prove that y is a subset of x. So the only way for two sets to be subsets of each other is if they're equal. That's why this works. And I'm just going to remind you that last time we learned that to prove that x is a subset of y, what you have to do is you have to prove that if x is an element of x, then x is also an element of y. That's what it means to be a subset. So you assume that little x is in big X, and then you prove that little x would also have to be in big Y. And so when you're proving that two sets are equal, you actually have to do that twice. You have to do it once here, you have to do it once here. Okay, so let us do some examples where we prove that some sets are either subsets or equal to each other. Okay, so let us look at number 2 here. So originally there were two parts. There was an A and B, and I've just done part B here, which is the sort of more formal proof. But what we're trying to show is that for any sets A and B, A minus B is always a subset of A. And so let's go ahead and try it. So remember, we're trying to show that A minus B is a subset of A. So we're going to start off by supposing that A and B are any sets. And then what we're going to do is we're going to suppose that we have x is an element of A minus B. So then what we're trying to do is show that if x is an element of A minus B, then x will also be an element of A. That's how you show that two things are subsets. So the answer to number 1 here is going to be, we must show that x is an element of A. The whole technique is you suppose you have some element in the first set, and then you show that it must also be an element of the second set. That's how you show two sets are subsets. Okay, and then where do we go from here? So by the definition of set difference is that minus thing, that minus in between A minus B. What that means, if x is in A minus B, what that means is x is in A, that's number 2, and x is not in B. That's just what the set difference is. So in particular, what does that mean? So remember what we're trying to conclude here. Our goal was to conclude that x is in A, and we have that x is in A. So in particular, x is in A, which is what we were trying to show. Okay, so this is a pretty easy one. In fact, it's sometimes these ones that are too easy can be a little confusing since you just directly get that number 2 implies in number 4. Let's try doing one that's a little more challenging. Okay, so this one is actually homework for you. So I'd like you to go ahead and try this. Pause the video and try this one right now, and then check your answers. Okay, and this is another homework one for you. So this one is a little bit long because what you're trying to do here is prove equality. But they have divided it up into the two parts, the two things that you need to do. So you need to show this subset relationship, and you need to show this subset relationship. Okay, and if you do both of those, then you'll have shown equality. This one, if you're thinking it looks too challenging now, maybe come back to it after the next couple of examples. Okay, let's look at this example. So for all sets A, B, and C, if A is a subset of B, then A union C is a subset of B union C. So I'm going to start by just defining what A, B, and C are. So let A, B, and C be sets. You always need to define your letters that you're going to use. Okay. Let A, B, and C be sets, and now I'm trying to prove an if-then statement, so I'm always just going to assume the if part. That's direct proof technique. So assume the if part, assume A is a subset of B. Okay, and now my goal is to show that we will show that the then part, so A union C is a subset of B union C. Okay, that's our goal. So how are we going to show that A union C is a subset of B union C? Well, we just talked about how you show that things are subsets of other sets. So the way you do it is you suppose that you have an element in the first one. So suppose X is an element of A union C. And now what you need to do is you need to show that, so we will show that X is also an element of B union C. I'll just note that these parts where I say we will show, like this is kind of optional. You don't have to put that in your proof. Sometimes it's helpful to kind of keep yourself focused on what you're trying to do. You certainly never want to put those statements in there without the we will show part. Like never just state the thing that you're trying to prove until you've actually proved it. But it's kind of up to you whether you put those type of like goal-oriented statements in there. Okay, anyway, so what we need to do is show that X is an element of B union C. How are we going to do that? So what are the things that we know about X? Well, we know that X is in A union C. And what else do we know? We also know that A is a subset of B. Okay, let's do it like this. So since X is in A union C, that means X is either an element of A or X is an element of C. Okay, so now let's break into cases because we have this OR part here. So my cases are going to come from the OR. So case 1, X is in A. So if X is in A, well, A is a subset of B. So that would mean that X would also be in B. And if X is in B, then X is also in the union of B and C. Okay. Now let's look at case 2. So case 2, remember it was coming from this OR up here. So case 2 is when X is in C. Okay, if X is in C, then X is in B union C. Because B union C, that would be all the elements that are in either B or C. Okay, so in either case, X turned out to be in the union of B and C. Yeah, so at this point you could finish up with a statement to the effect of, therefore, A union C is a subset of B union C. But that's optional. You know, it's pretty clear that was the goal of the proof. Okay, so here is a homework problem for you that is extremely similar to the one I just did. In fact, I think it's actually a little bit easier. So I'll let you work on that one and then check your solutions. Okay, let's look at this example, number 19. For all sets A, B, and C, A cross B intersect C is equal to A cross B intersect A cross C. So it starts with a for all statement. So as usual, I'm just going to translate that into a let statement. So let A, B, C be sets. Okay, and now I'm trying to prove that two sets are equal. So what I need to do is first show that the left-hand side is a subset of the right-hand side, and then in the second part I'll show that the right-hand side is a subset of the left-hand side. So first we will show that A cross B intersect C is a subset of A cross B intersect A cross C. So how do we show that a set is a subset of another set? Well, as we've been doing, you let some element x be in the smaller of the two sets, this one. But in this case, it's a little bit tricky actually because this is a Cartesian product. So if I just say that x is in A cross B intersect C, that element x is actually an ordered pair. So it's easier for me if I just assume that I have an ordered pair to start with. So what I'm going to do is I'm going to assume x, y is an element of A cross B intersect C. You could still just use x, but unfortunately you would still need to say that x equals some other letters, an ordered pair, like maybe x would equal the ordered pair of A, B, or something like that. You definitely need to work with an ordered pair at some point because the set that we're talking about is a Cartesian product. Okay, so what do I get from the fact that xy is in A cross B intersect C? And what am I trying to do with that information? Remember, what I'm trying to do at this point is we will show that this ordered pair xy is an element of the right-hand side of the equation, A cross B intersect A cross C. And that's an optional statement for you to put in your proof or not, as you feel comfortable. In any case, that's what we're trying to do. Okay, so what information do we have to work with? From our assumptions, we have that xy, the ordered pair xy, is an element of A cross B intersect C. So because of that, that tells us quite a bit, actually. So an ordered pair in a Cartesian product, the first element of the ordered pair has to be in the first part of the Cartesian product. So x has to be in A. And the second element of the ordered pair, y, has to be in the second part of the Cartesian product. So y has to be in B intersect C. And then based on that, because y is in an intersection, we know even further that y is in both B and C. Okay, so that's all the information we can extract from the assumption. So now let's look at what we're trying to show and whether we're prepared to do it yet. So we're trying to show that the element, the ordered pair xy, is an element of A cross B intersect A cross C. So to do that, to show that it's in that intersection, we need to show that xy is in A cross B and that xy is in A cross C. And I think we have that. So let me just write it up. So since x is in A and y is in B, that tells us that xy is in A cross B. And then furthermore, since x is in A and y is in C, that tells us that xy is in A cross C. And then finally, since xy is in both of those sets, since xy is in A cross B and in A cross C, it's in the intersection of those two sets. So xy is in A cross B intersect A cross C. So that's the end of part 1. And now what we need to do on part 2 is we need to show the following. So we need to show that the right-hand side of the equation is a subset of the left-hand side of the equation. Still having trouble adjusting to using this pen. So we need to show that A cross B intersect A cross C is a subset of A cross B intersect C. Okay, so how do we do that? We're going to assume or suppose that we have an element that is in the smaller of the two sets, this one. So suppose, and once again I'm going to use an ordered pair. Instead of just x, I'm going to use xy. So suppose xy is in A cross B intersect A cross C. Okay, and then what do we need to show? So we will show that xy is in A cross B intersect C. And that's kind of an optional goal statement there for you. Okay, so let's use what we know from our supposition. So because xy is in A cross B intersect A cross C, that means xy is in both of those two sets. So xy is in A cross B, and xy is in A cross C. So from that we can tell that x is in A, y is in B, and y is also in C. So what can we tell from that information? Remember where we're trying to get to. We're trying to show that xy is an element of A cross B intersect C. So to show that, we need to show that x is in A, which we already have, and that y is in B intersect C, which we mostly have, but we could point that out at this point. So y is in B intersect C. So xy is in A cross B intersect C. Okay, so here is a homework problem for you guys that is very similar to the last one that I just did for you. So go ahead and try this one out and then check that you've done the solution correctly with the back of the book. Okay, the final new material for today's lesson is how to prove that a set is empty. So if you want to prove that a set is empty or that it has no elements, the way you do that is you just simply suppose that it does have an element and then derive some kind of contradiction. Whatever that contradiction might be, that will invalidate your supposition that the set had an element. Okay, let's do an example. Okay, let's look at this example. I'm going to show you how to prove that a set is empty. So we have a for all statement here for all sets A, B, and C. So as usual, I'm going to translate my for all statement into a let statement. So let A, B, C be sets. Okay, and then I'm going to try to show that this set right here is empty. So the way to do that, I'm going to suppose or assume or let x be an element of A minus C intersect B minus C intersect A minus B. And then I'm going to try to show that that leads to a contradiction. So what do I get for this supposition? What has that gained me? I actually get quite a bit from that. So because it's an intersection of three sets, that means that x has to be in each part of the intersection. So x has to be in A minus C, and x has to be in B minus C, and x has to be in A minus B. So I don't see any contradictions yet, so let me keep going with this and I'll drill down into each piece of information that I'm getting. So since x is in A minus C, so I'm going to try to use this first piece that I got here. What does that tell me? That means two things. X is in A and x is not in C. Okay, and I still don't see any contradictions, so I'll keep going with translating the information that I've gotten so far. So this next piece of information, since x is in b minus c, that tells me that x is in b and x is not in c. Okay, I still don't see a contradiction, so let's keep going with this third thing that I got. So since x is in a minus b, that means x is in a and x is not in b. Okay, I think I see the contradiction here. So previously I had said that x was in b, and now I'm saying that x is not in b. That is a contradiction. So I'm just going to point that out. Contradiction. X can't be in b and not in b. Okay, whenever you get a contradiction, all that means is that your supposition was wrong. So our supposition was wrong. That means there is no x in the set. So that set must be empty. And the way that you say that a set is empty is just say that it's equal to the empty set. Okay. This kind of part's here at the end. After you find the contradiction, I would say all of that there is kind of optional. It just depends on how much you want to try to explain. As soon as you found the contradiction, then from there it's pretty clear that that means the set should be empty. Okay, everybody, here's a homework problem for you to try. It's a fill in the blank, and the statement that you're proving is quite similar to the last one that I did. And here's your last homework problem. It's quite similar to the last ones that we had done, the last homework problem and the example that I'd done. Just a word about the quiz next time. I think it'll probably be fill in the blanks proof, which will be done on Blackboard, similar to today's quiz. So look forward to that and study hard, and thank you for watching my video.